let's talk about the photoelectric effect. So what is that? Well, when light falls upon certain metals, then electrons are ejected, which, just think about what I just said there. You take like a flashlight, you shine it on metal, and then all of a sudden electrons just start floating out of it. So hopefully that sufficiently communicated to you how crazy that is, that you just can shine light on certain materials and certain metals, and electrons are just, they just bounce off. So why does this happen? Like, what can we even do to explain this? Because if light is a wave, right, and it's traveling in a wave, how is it interacting with the electrons here to make them jump off, right? This is matter, this isn't matter, but they're interacting. So how is that working? So how they figured this out, because Hertz was investigating electromagnetic waves, so he had this apparatus called a photocell. And basically what a photocell is, it's this. So this is like the photocell part. And so it's an evacuated space where there's nothing but these metals, but there's no other particles in the air, okay? And then you shine light on one of the metal parts, and then what happened was that there was an ammeter reading. But of course, when it's just in the dark, there's no ammeter reading. There was nothing making electrons flow, because if you look, there's a battery here, but since there's a break here in the photocell, there's no connection. There's no way for the electrons to keep flowing. They just go here, and you get an excess on that thing. And then as soon as light was shone on this plate, then there was an ammeter reading. There was a reading on this ammeter that there was current going through, which is pretty interesting. So what we came up with is that electrons must be ejected by this electromagnetic radiation. They must be flowing across the photocell tube, and then of course they keep going here, because they are obviously going to flow along a conductor, but across space with nothing there to really make them flow is pretty crazy. So the thing is, this doesn't really go with our wave particle of, or our wave theory of light, okay? So let's talk about how we could explain this, because wave theory couldn't explain this. So here's what wave theory thought about light. Number one, if light intensity increased, remember, light intensity means brightness, and the number of electrons ejected here and the maximum kinetic energy that they have should increase. So more intensity should increase how many electrons are ejected and their kinetic energy, basically their speed. And they thought that because higher intensity light just means that the photons have a greater electric field amplitude, so therefore they should have a bigger ejection velocity. So that should obviously just make that happen. And they said that the frequency of the light shouldn't affect. So you can change it from red light to blue light. That's not going to affect anything. But if you have dim red light and then change it to bright red light, that should change it. Okay, so that was what the wave and classical theory said, but that wasn't actually what was happening. So that's why we came up with a theory of photons and the fact that light can act as particles, because it does. So this is what's actually happening, is that a single photon can cause a single electron to eject. Okay? So if the light intensity is increased, then more photons are incident and therefore more electrons are ejected. Okay, so that's really important. More light intensity means more photons. And it's really, really important that you are able to put those two together. Okay? However, the energy isn't going to be affected by intensity. What is the energy going to be affected by? It's going to be affected by frequency, because we know energy of a photon is affected by its frequency, not its intensity. Okay? So they also found out that certain frequencies of light didn't even eject electrons, right? In some metals, they tried to shine red light and there was no electron flow, but then they shone blue light and there was electron flow. So it has to be above this threshold frequency, which we're going to talk about a little bit more. But once the threshold frequency was reached, then if you increase the frequency beyond that, then the kinetic energy increases as well. Okay, so that means the energy of the photon is transferred to the electron. What affects the energy of a photon? Increasing the frequency increases the energy of a photon. Therefore, that increases the energy of the electrons going across the photo gate, right? Because we know they are directly proportional here. Energy of the photon is directly proportional to the frequency. So again, if frequency goes up, then the energy of the photon goes up, and therefore the kinetic energy of the electron that it's ejecting goes up, because all that energy is being transferred, or at least a bunch of that energy is being transferred to the electron, okay? And that is the actual explanation of what's going on as the photon theory, because they noticed, oh, intensity isn't actually affecting how much energy it has, but frequency is, okay? So frequency determines if the electron is ejected, okay? So we do need a certain frequency, and it's different for all types of metals, so we'll go over that. But the intensity does determine how many electrons are ejected, if it's as long as it's above the threshold frequency, okay? So if you have red light, and it's not ejecting electrons, it doesn't matter how bright you make that red light, it's never going to eject any electrons because it's obviously not above the threshold frequency. But say you shine a green light and electrons are ejected. If you make that green light brighter and more intense, then it will have more electrons being ejected. They just won't go any faster than they were before, okay? So this supports that theory of wave-particle duality of light, because do not discount. We just went over an entire unit that showed you how light travels as a wave. It absolutely does act as a wave. It diffracts, it refracts. Only waves do that. Particles don't do that. So therefore it's definitely a wave, but then we have some situations here where, it kind of seems like it's acting like a particle. So the thing is, at this point, we still don't fully know, okay? This is still under investigation, but the current theory that we have is that light travels as a wave, but it interacts with materials as a particle. So it's kind of like a wave that acts like a particle. So of course, dim violet light, since it has that really high frequency, it does have a lower intensity. It can eject fewer electrons, but with a higher energy. And then bright red or orange light, it has a lower frequency, so it won't necessarily be able to eject electrons, okay? It depends on the metal that you have. So even though it has a higher intensity, sometimes it won't even eject electrons, right? Because, for example, if we have potassium, this red light isn't above the threshold frequency. It needs a minimum amount of frequency, i.e. a minimum amount of energy to interact with the electrons. So if we shine red light, nothing's going to happen. But you shine green light, then we have our electrons being ejected. Woohoo! And then if we shine blue light, then we have electrons being ejected. And at a larger velocity as well, because it has more energy, because blue light has more energy. All right, so in order to for a photon to eject an electron, well, of course, we know that electrons are held in metal by attractive forces between the electrons and the nucleus, but we also know metal. What do we know about it? It's a conductor, so therefore it doesn't hold on to its electrons as tightly. So our photon has to have a minimum threshold energy to eject the electron. So we call that the work function. And that is, of course, the minimum amount of work needed to eject an electron, or amount of energy needed to eject an electron. Okay, so that we call that W naught, this little zero down there. Okay, and that's equal to H Planck's constant times the threshold frequency, which again is different for every metal. So that's something that would be given to you. Okay, so there we go. W naught is our work function in joules. H is our Planck's constant in joules times seconds. And then, of course, our F naught is our threshold frequency, so the lowest frequency at which electrons can be ejected from a certain metal. So here's an example. Okay, so if we have a few different metals here, so cesium has a pretty low threshold frequency, right down here at about 5 times 10 to the 14 hertz. But something like mercury has a really, really high threshold frequency. So you definitely need to shine blue violet light on it or beyond that. Okay? So what happens when the photon hits the metal? Well, the photon is completely absorbed as the electron is ejected with kinetic energy. So that photon's energy has been completely absorbed by the electron. Okay? And we know that energy in has to equal to energy out. So we have the photon energy is the energy going in. And then the electron needs to take some of that energy just to release itself from its nucleus. And then the rest of the energy left over is the kinetic energy of the electron. So that tells us that the electron's kinetic energy that it has is the original photon energy minus how much energy it took to eject that electron, which is the work function, right? The energy that's needed to eject the electron is what we call the work function. Okay, so the maximum kinetic energy that an electron that's been ejected can have is that energy of the photon minus the work function. So we have HF minus HF naught, right? So 2 instances of H. Okay, you can also express this in terms of the wavelength. If you don't have the frequency of the light, you can have the wavelength of the light. If you need to find the velocity of the electron, then you can translate EK into 1/2 mv squared. You do have mass, okay, on your data sheet of an electron, so we're going to be using that. So that's another form in which we can use that equation, okay? But this is the work function. This is really, really important that you know this, okay? That is not on any sort of data sheet or anything like that. The individual equations are there, but that equation is not there. So again, when we're looking at this photoelectric effect, you just have to think sum of energy in is equal to the sum of energy coming out, and then you can rearrange from there. So we're usually able to measure the maximum kinetic energy of the electron because we can kind of use the voltage that's making the electron stop. So they'd take this photocell and then they'd let the electrons flow, and then they'd put a voltage on it to see how much voltage was needed to make the electron stop, okay, and turn around. So that's kind of what they did there to see what's the maximum amount of kinetic energy, right? Because if the electrons were still hitting this plate, even though it had a voltage on it and a negative charge on it, because obviously then the electrons would want to go back the other way, then there wasn't enough energy to make it stop. But if the electron stopped, then obviously we have enough energy to make it kind of go back the other way, back where it came from. Okay, so that's what they did to figure out that maximum kinetic energy. So they just changed that voltage until they got right to the exact point that the current stopped. Well, we know how to calculate stuff with voltage and stuff like that, don't we? I know, we got to go back a little bit to our electric unit, okay? This is basically just saying everything I did. But when those electrons are stopped, that's what we call our stopping voltage or stopping potential, okay? So that loss of kinetic energy is equal to your gain of potential. So that maximum kinetic energy is equal to how much potential energy was needed to stop it, which is, of course, the charge times the stopping voltage, okay? And then, of course, we know kinetic energy, we were able to find that using energy of the photon minus the work function. So that's another equation that you can kind of derive using this, okay? So there's a lot of equations that can be put together here, so be ready for that. It's going to take a little bit of work. So That's all the information, but let's just go on to do a few examples because I think that's probably going to help you understand this a lot better. All right, so here we have barium that has a work function of 2.48 electron volts. So since that's given to us in electron volts, remember that is a measure of energy, and that is fine. So we want to know the maximum kinetic energy of the electrons if the metal is illuminated by light of wavelength 390 nanometers. So this is likely in the violet, ultraviolet spectrum. So we want to know what's the speed it's left it with. Okay, so again, remember, this is the kind of thing where you're going to have to come up with this equation on your own. So we know that energy in is equal to energy out. Okay, that's all we need to know. So what's the energy going in? It's the photon. And then, of course, some of that goes towards ejecting the electron. Okay, so remember, that's what we call the work function. And then the rest of the energy goes towards the kinetic energy of the electron. Okay, so photon energy is either HF, or since we have our wavelength here, we're going to use HC over lambda here, is equal to our work function. We're just going to call that W naught here. I don't think I need to do HF because it actually just gives us our work function in electron volts. And then we have our kinetic energy. Okay, so we want to know the speed, so therefore, obviously, we're going to need to find the kinetic energy. Okay, and then that's going to help us find the speed from there. So my kinetic energy is just going to be HC over lambda minus the work function. Okay, so here's the thing is I can start by finding the kinetic energy in electron volts if I want to, because I can find this HC over lambda if I use the electron volt version of Planck's constant. Then I can have that in terms of electron volts, as long as it's all in the same thing, okay? So since the work function is already in electron volts, let's find the energy of the photon in electron volts, and then we will need to convert that to joules in order to get speed, okay? Okay, so when we do that and calculate our kinetic energy, we should get 0.705 electron volts, okay? But since we do want their speed, we need to convert this into joules. Remember, you have this conversion on your data sheet. So many people forget that they have this, but you do. It's 1.60 times 10 to the negative 19 joules for every 1 electron volt. So that gets us a kinetic energy of 1.13 times 10 to the negative 19 joules. So now that we have that in joules, we need that to be in joules if you want to get speed. Okay, and now I can go up and calculate the velocity, because we know kinetic energy is equal to 1/2 mv squared. Okay, so we're going to solve for the velocity here, which would be 2 times the kinetic energy divided by m, all square rooted. Okay. And when we do that, we get 4.97 times 10 to the 5 meters per second. Okay, so there we go. We found the speed of this ejected electron right there. So I know it's a bit of a step getting there because you don't necessarily have this exact equation. So always start from here. Whenever you're working with the photoelectric effect, start from here. Okay, energy in equals energy out, and then you're going to have to kind of figure out how to break it down the way you need to from there. But let's go over another example just so you can get used to this language a little bit more of work function and things like that. So we have a photoelectric effect experiment. It's observed that no current flows unless the wavelength is less than 570 nanometers. So that didn't give us our threshold frequency. It did give us, however, our threshold wavelength, I guess we could call it. Okay, So first we want to know, what is the work function of this material? Well, we know that the work function is equal to H times the threshold frequency. But again, we don't have that threshold frequency, but we have the equivalent with the wavelength, right? Because the frequency is C over lambda. There we go. We can calculate that, no problem. So let's do that. Here I'm going to use joules for H. If you don't know when to use joules, when to use the EV, if you don't already have EV, you're probably using joules, okay? And this one is, if you have meters and seconds and all that stuff, you're likely wanting to use joules. Okay, doing that, I get a work function of 3.49 times 10 to the negative 19 joules. And if you need to convert that into electron volts, you can, using the fact that 1.6 times 10 to the negative 19 joules is 1 electron volt. Okay, there's the work function. And now we want to know the stopping voltage required if light of wavelength 400 nanometers is used. Okay, so again, what does that mean, stopping voltage? It means all that the kinetic energy that the electron has to be converted into that potential energy, but of course here it is electrical potential energy. What was kinetic energy of the electron? Remember, it was the energy of the photon to begin with, minus the work function. And of course, our potential energy is the Q times the stopping voltage. Okay, Q being the charge. How do you get the energy of a photon? Hc over lambda here, because we do have the wavelength, not the frequency. We just calculated the work function, so I can just keep that there, and we get QV stop. So we're looking for the stopping voltage, and we do have everything else. We have Q, so we can figure this out without much trouble. So I'm going to do that. I know that doesn't look the best. I accidentally struck through the 400 times 10 to the negative 9, but really I'm just taking that whole thing right there and dividing it by the charge of an electron. And when we do that, what do we get? We get 0.927 volts. Okay? Easy as pie, right? It's okay. I know it's not easy. That's why you just got to do a lot of these. And then you will kind of get the hang of it, because there is just stuff you've all seen before, but now it's just putting it together in a completely new way. Okay? Just to give you a little bit of context, here's a few old diploma questions about the photoelectric effect. Okay? Because a lot of people have a hard time figuring out what was the classical wave theory again, and then what did quantum physics come along and explain. Okay? So here's 4 photoelectric effect predictions, and you have to sort them into classical wave theory and quantum physics. Which of them was the classical wave theory that predicted it, and which of them was the prediction from quantum physics? So honestly, here you just read it one by one and sort it into which category it needs to go into. So low intensity electromagnetic radiation incident on a photoelectric surface for long periods of time will cause photo emission. So low intensity incident on a photoelectric surface for long periods of time will cause photo emission. So remember, does intensity have to do with whether it's emitted or not? No, that's frequency. We know it has to be at least at the frequency. That was definitely part of the classical wave theory, because they thought intensity would affect everything. Okay? So that is part of the classical wave theory, not quantum physics. 2, high intensity electromagnetic radiation will not cause photoemission unless its frequency is greater than the photoelectric surface, threshold frequency. As soon as you see that, you're like, yep, that was part of quantum physics. So there we go. 2 goes in the quantum physics category. 3, the energy of the emitted photoelectrons will increase if the intensity of the incident electromagnetic radiation is increased. Is that what's actually happening? No, it's not. Remember, that was wave theory because they thought because the electric field would have a higher intensity, then that would mean that the electrons would have a higher intensity, and they were wrong. So that's part of the wave theory. And then 4, obviously, it's going to go, but let's just make sure we understand it. Energy of the emitted photoelectrons is independent of the intensity. Independent of intensity, yes, it absolutely is. That is our quantum physics right there. Okay? Just note, wave theory didn't completely get it wrong. They did predict that intensity would affect how many electrons were ejected. They just didn't predict that intensity would have no effect if it was underneath a certain frequency. And then they also thought that intensity was going to affect its energy, which it absolutely doesn't. Okay, so they did get one thing right, and that is that intensity does affect how many electrons are being ejected. But it's just as long as they're above the threshold frequency. Okay, so there you could have a bunch of different answers. Let's just go over one more. A group of students produces the following observations relating to the photoelectric effect for light that's incident on a surface. So, here are their observations. Light that has a frequency less than the threshold frequency for that surface will not result in the emission of photoelectrons from the surface regardless of the intensity. Okay. For light that has a frequency higher than the threshold for that surface, a more intense light produces more photoelectrons than a less intense light. Yep, we know that's true. The intensity of the light has no effect on kinetic energy of any photoelectrons that are emitted by the surface. So using classical wave theory, students can explain which one. So which one did I just say that the classical wave theory got right? Remember, they thought that intensity was going to affect everything, and the only thing they had right is that intensity affects how many electrons are ejected. So which one does it say? Here it says more intense light produces more photoelectrons. That is the one that they predicted. And then, of course, everything else. They didn't say anything about threshold frequency. The wave classical model couldn't explain that. The wave in classical model actually thought that intensity would mean there's more kinetic energy, which there's not. So it didn't explain 3 either. So only observation 2 could it have explained. So our answer there is B. All right, you guys, that's all I have for you. I know that's a lot today. It's definitely a big part of this unit. So it's really, really important that you work really hard, go over the notes again, do a bunch of the questions just so you can have a lot of practice at this, okay? If you have any questions, please let me know, and I'll talk to you later.